I would request again to take down whatever references giving you. The final topic is reinforcing 3D printed concrete members. Very, very open topic. Lots of challenges, ripe for so many different PhD theses. But I would caution one thing. A, a work on reinforcing should be applied to why do you need to reinforce 3D printed concrete and how you need to reinforce. Randomly reinforcing with a steel bar like you reinforce a regular rectangular beam and studying a 3D printed rectangular beam with one bar in it and doing a ASTM G09 test is a waste of everyone's time, right? It is not going to work. You have to think about why do you need reinforcing. If I'm doing more compression control structures, then to control cracking and stuff like that, can I do fiber reinforcement and stuff like that, and use the compression capacity of the material and the shape that you do to generate all that you want? Versus when you really need, maybe external pre-stressing is the way to go. Maybe that's how you should do it. In between interlays, maybe textile reinforcement is the way to go. So there are so many different options that you can think of and do, but they're all going to be restricted to how you design your structure. So if you take your IS 456 and design a simply reinforced rectangular beam with 3D printing and drop in n number of rebars at whatever spacing that you have, you are losing the game big time. Correct? So think of reinforcing in that context. It is a really different ball game, and that's why people are having difficulty. So I'll give you some very generic ideas. I have done zero work in this area except for some work in fibers with fiber reinforcement. So all that you see are what is available in the literature. Okay. So and I have put in all the references as well for you to go through and look at all of this. So reinforcements, what are the kind of reinforcements you have? Short fibers, random orientation, fibers with oriented ways, cables and yarns, unidirectional bars, textile meshes which are bidirectional, and even cages that are 3D. People have even used reinforcement cages. Not really steel bar reinforcement, but mesh reinforcement as cages and do it. So lots of different ways in which you do it. But at the end of the day, you reinforce for a function, and the function has to come based on your design, and therefore the reinforcement should follow your design. And the design is not going to be a prismatic member that is conventionally reinforced, because if that's the case, you don't need a 3D print. You can simply put the rebar and pour concrete. There's nothing easier than that. We all have done it for centuries. All right, so here is reinforcement in conventional concrete construction. Very easy. This is somebody who, you can look at that. So it's a paper narrative manufacturing. So they look at 10 advantages of extrusion-based printing. I don't know why 10, they could have added more. And then the systems-based approach to evaluation of reinforcement strategies. And they came up with a very nice, even though mostly an academic, but useful framework to find out the suitability and degree of system integration of various reinforcement strategies. Not surprisingly, right? There should be common sense. What is the best strategy that they find out? Fibers. Of course, right? That's the best strategy. That's what, in terms of suitability and degree of system integration, and then additively manufactured rebar. So as you print your concrete, you have another extruder that extrudes steel also, which means you have a 1600 degrees Celsius melt of your material coming into extrude. Don't know how that happens. You can do it. Or you can do an FRP extrusion. If you're using fiber reinforced plastic, you can do fiber FRP polymer extrusion along with rebar. But all of those will get infinitely complicated. You look at how organized and how many different activities have to go. So think about this very simple idea, right? You have to keep on extruding one layer, and then the layers right below have been printed and they are covered with gunny bags that you saw yesterday. They are spraying water. While you are spraying water to prevent shrinkage cracking, can you think about a fiber reinforced extruder coming along with it and getting sprayed with water? practically there are several challenges of co-extrusion. Theoretically, in a lab, sitting in a nice computer picture, co-extrusion is great. You can say, yes, I have small scale systems that I can put on the back of a truck, bring it to the site. I have a spool of my polymer. I need only 100 degrees Celsius kind of temperatures to melt it, and then some kind of an extrusion pulling, all of that. I can do all of that. 100 degrees Celsius to get it from a space heater is not a big deal. Theoretically, this is beautiful. But think about polymer wire coming in and you spraying water right on it. Why are we doing it, right? So there are lots of practical challenges in co-extrusion. So at the end of the day, what will work is what has worked traditionally, fibers being the best, entrain it with it, put in rebars whenever you have to, if you have to, or figure out your structure, make your structure, and then externally reinforce it, externally pre-stress it later. But external reinforcement is always a problem. If you're suspecting vandalism, external reinforcement is a big problem, because that's what is taking all the tension, and you have a bridge structure that's externally pre-stressed. You don't know if somebody goes and cuts a pre-stressing rod in the night if it's externally reinforced. Then you have to think about covering that externally reinforced one. Lots of challenges, right? Again, so more challenges than solutions. Pre-installed wire meshes. You can see here pre-installed meshes, and you can see this nozzle printing in between the wire meshes and squishing the concrete so that the concrete goes in between the meshes too, and then you keep building it up in a way that both these nozzles squish enough, and the layers join each other, right? So two nozzles come together to form one layer. Two nozzles are coming together because there is rebar in between, and then the concrete comes in between. Frankly, if you ask me, I would do a form work if I need that. Correct? It's difficult. It's challenging. It's difficult. I mean, you can do it. How much of coordination, how much of work is required? You can do it. It's not that you can't do. Reinforcement integration during printing. Here is another mesh. So see what you have completely redesigned the nozzle. The nozzle now has a lip in the middle, right? Where the mesh is. So you have to position the mesh exactly straight, because your printing path is, or straight, or whatever that direction is, your printing path is that direction. So if you manually place that mesh, and if you have a 1 millimeter tolerance difference, at one point of time, your nozzle is going to hit the mesh. So it has to go very precisely through it, which means what I told yesterday, tolerances becomes extremely important. Have we been able in the concrete industry to get to 0.1 mm tolerances? Have we been able to do that? When we are able to do that, this will become an interesting idea. Until then, I can do in the lab. Again, I can do linear things with reinforcement. The moment I have a curved section, now I'll have to have a bar bender coming in and doing it. It's the same problems that I end up with in rebar in concrete. So more challenges in that zone. But again, people have done all of this in a laboratory reinforcement. Now, weld joints of reinforcement. So I have vertical reinforcement, no problem. I'll put it with horizontal reinforcement. What do I do? When do I go and tie this thing? I can't tie something in, because a tie is going to be something that will protrude out. Now my printer will not extrude carefully. Now I have to go and weld there, right? Adds another layer of complexity. This is very easy. If you can do it well, I can extrude fibers through. Fibers will come out well, oriented direction. So again, that's why we all love use of fibers, which is probably the easiest way to incorporate reinforcement. You can put 3 filaments, and I can put in pieces of rebar like this, piece of rebar like that. I can do all my artistry and show my artistic abilities in a layer of reinforcement. People do that. Put in 3 layers, and one guy walks in and puts steel, and then keeps printing. Another guy comes and puts. You can do all of that. That's also possible. It's not that it's impossible. But again, what is one of the biggest advantages of 3D printing? Reduction of labor. What did you add now? One guy to come and walk along with the printer to put rebar. You're losing another advantage. So there is nothing that you gain without losing something. There's always a compromise. That's a choice that you have to make. Like I said, I'm not here to give you the answers. I'm here to show you the problems. Reinforcement integration during printing, the other thing. So here is Here is a cut section of something that was printed with reinforcement. You see that unevenness on the sides? It's not going to be bonding to steel really, really well. So that's another issue. Here is an additively manufactured reinforcement. So reinforcement itself is all additively manufactured while you're printing it, which means you have a steel company right next to your printing process as you do it. Of course, in a small scale laboratory setup, you can do whatever you want, right? I can create a Mars vehicle and say that I've gone to Mars here in the lab. When you go there, you will figure out what it is in the lab because you have plenty of oxygen. You are not worrying about that. You created the temperature, you created the harsh roughness in it. You forgot the oxygen alone. But if you go to Mars, you don't have that. The bigger problem is what you have forgotten, the one that you forgot, correct? All the easier ones you solve. That's what we do in the lab most of the time, right? I solve a problem in a condition that is most convenient for me to solve, and you ignore the bigger problem that is in the field. I've gotten 200 megapascal concrete. Well, how did I do it? I was sitting for half an hour consolidating this small piece of a cube. Then I'm sitting and consolidating, and I get so much of strength. In the field, I forget that I don't make 5 specimens. And in the field, I forget the fact that I can't consolidate 10 cubic meter of concrete sitting like this. Labs, you can get lots of things. So translation is where the issues happen. So here is one example of external reinforcing. So here is a truss system, very similar to the truss system that you saw. They printed the truss system and then had external cables. You see this external cables reinforcing it? External reinforcement. The problem is, I can go and put in the field and somebody comes and decides to cut this external reinforcement. My structure has no more stability, no more strength in it. So vandalism is a big problem, and structural vandalism is structural fire, structural, people breaking things, very common all over the world. Here is another way. This is another common way of doing it. But if you can create, you saw those walls yesterday, right? Double white walls. And then if you want to have earthquake protection, for example, lateral resistance, if you are in earthquake zone, you can put in rebars like this, vertical rebar, and then grout the whole thing, right? So I can take these two whites, put in rebar, and grout the whole thing. Now, what have I done? I have made a solid concrete wall, correct? I could have done a hollow block masonry and reinforce with masonry. I may be cheaper, correct? Unless I'm looking for a really, unique shape. I have no benefit in 3D printing and putting this. I now do a 20, 30 megapascal concrete and then put in rebar and put in another 40 megapascal concrete inside it, making this 40 megapascal concrete just a lost formwork, right? This is now basically formwork that I've lost. It's doing nothing. So do we have to do that? Are there ways of doing it better? Again, we do all of this. I have done this too in one of the buildings that we built in Tempe. At that time, the only way we could get Codal, the local guy, to accept the building was to print the walls and then every 6 feet have columns, physically basically put rebar and grout in between, basically leaving the rest of my 30 megapascal concrete useless in terms of load carrying capability, because the entire load now comes where? The columns. The rest of it is just sitting there watching. Drying shrinkage, no problem. Let it shrink. It's doing nothing. Why don't it? It can shrink. It can do whatever, right? But again, the practical problems in dealing with these materials. Reinforcement strategies using steel bar. Here you see here, again, the shape, different shapes. But what they're doing is, after they do a certain number of layers, they are putting in rebars. Okay, so you print these layers, you put these rebar and rebar cage now, and then you get this. How did you get this from this? Any idea? Shotcrete. Shotcrete on the surface. So you basically print a layer, do the rebar, put all the rebar as per the design, and then shotcrete on the surface. So you get your structural shape that you want. You get it done faster because shapes can be done only by printing. You get that shape faster. You have the rebar problem. You need reinforcement. You put the reinforcement. You shotcrete. Unique structures. possible. Meshes and cages, again, you remember this one I told you, right? You have a rebar mesh that's put in, but then two nozzles are coming in and doing it, which means you can do it straight, but as long as you start to curve, you will have a problem with shapes. So straight structures, you can do more of this nicely. We've seen this here. Here, metallic grits and mats and cages are all being done. Here is a way where cables are being interlaid through nozzle and interlayer integration. So you see here, nozzle is putting your concrete in, and then a cable puller is pulling a cable on the layer below. You see that? So you have a cable puller putting the layer, and maybe once you end it, you might cut it, and the cable won't be there anymore. But then the concrete will go continuously. So basically, what you have done is, instead of a man placing a rebar, you have an automated machine placing a cable. Process principle exactly the same, and you can do that as well. And here is where another way in which you have put in rebar and placed the same way. You have these two different nozzles coming in and covering the rebars. So you can do that as well. If you have lots of different meshes, then you adjust your nozzles in such a way that you can drive through this is like web getting more and more complicated, right? Mesh insertion. This for short fibers, as I said, easiest, best, most comfortable way, doesn't interfere with your shape of your construction. You can use however you want. But again, fibers have disadvantages. If they're short fibers, they're discontinuous. Load transfer is not continuous. If you want like a rebar continuous load transfer, fibers will not do it. So they have their own disadvantages as well. But the advantage is it won't interfere with your shape. It won't interfere with your printing. All you need to take care of your rheology of your mix. Make sure that your fibers are of the right size. Your nozzle size are controlled to make sure that the fibers are aligned, and you're good. Most cases. The other interesting ways, I showed you this, where you print a few filaments and then you physically place reinforcement in whatever direction you want. You can here is where you can do steel bars, penetrate them. So you build all these layers up, and then you figure out that I need reinforcement. So you take a steel bar and squeeze in through your concrete. Tell me what will happen if I do that. Well, if I do it very, very, very carefully, it may not collapse. But then I'm disturbing the concrete and I'm disturbing the layers, and I have to do it before it sets completely so that I don't exert extra pressure and crack the inner layers. It all has to be so coordinated. And even if I drill it, I have to be so very concentric in the process. Even a slight eccentricity in movement is now going to create a gap that is slightly larger than the size of the reinforcement. Your bond is gone completely, which means it has to be extremely done with so much of precision. So people said, okay, that's more complicated. I'll find another way. I will screw this down, right? That's now even smarter. If you screw it, here it's a helical motion. Now I'm really not having that problem. All I need is the way that you drill a screw into your wall, right? Your motion is axial. Your motion into the wall is helical. When you have helical motion, what happens? The force that is exerted is going to be smaller inside, and there is going to be that continuity within where the bond is actually a little better. But then what do you want? You want a screw-like reinforcement to go in a helical way. So that's another way of doing it. And then here is a shotcrete 3D printing process. That's a vision. So they clearly said it's a vision of how another, while you're printing your stuff, another guy will come and keep on poking this and keep on reinforcing it behind you. So you keep on printing and the other robot will come and so this collaborative robotic business is a big deal now. They do so lots of activities, so lots of places that do robotic research, and we also have in the university robots playing soccer. Collaborative, right? Because one person cannot play soccer. So two robots are playing soccer. So they've programmed it in such a way that they've programmed the path of the ball, and the robots will collaboratively go and kick. So collaborative. In construction, robotic collaborative path, they do it in cranes a lot. in big, large construction sites, when you have multiple cranes operating, you want the cranes to hit together each other on the, you've seen all of them in the sky, right? So they do path planning of cranes in 3D, collaborative path planning. They do the same thing with robots and collaborative path planning. So if you have a big multiple structure, large structure, one of these things will do this job, the other one will be will coordinate with the path of the initial one and do what is required. A big field, they do a lot of work with this. Robotic assisted surgeries, collaborative robotic assisted surgeries are also being done. So lots of those things. Many of these are not from a civil engineering perspective or even a robotics perspective. These are coming from several different fields, and of course, how to adapt that to our field is the kind of question that we look at. So penetrating elements create a cross-layer anchorage and shear transfer. Some of the process flow examples of how to do that: placement of reinforcement during shaping. How does a multi-step process look like? Contiguous placement of reinforcement prior to concrete shaping. So lots of different ways in which, again, what this requires is not going in the morning of your printing to figure out where to do it. All of this will require lots of planning ahead of time on how to do this. Split flow nozzle, I showed this a little earlier. So here is how the nozzle will look like. So here is your mesh rebar that you have kept in, and the nozzle flow. So remember, in the previous one, I showed you two nozzles. Two nozzles coming in, squeezing enough so that material will flow. Can anybody think of Wednesday and Thursday and tell me what the problems would be in that case? When I say Wednesday and Thursday, what did we do most on Wednesdays and Thursdays? Rheology, right? So when two of them are extruding, and then I'm leaving a space in between and expecting the concrete to squish and push between them, what do I need? I need much more flowable concrete. What is a problem when we have much more flowable concrete? Shape stability is going to be a problem, correct? You're not going to be able to retain that shape well. If shape stability is a problem, what is the next immediate problem? Buildability will be a problem, right? So yes, I have solved the problem where I can put a steel and let the concrete flow and join, but then I am now sacrificing my buildability and shape stability. So that's a problem with two nozzles. So they were smart enough and said, okay, that's a problem. Let's do it with one nozzle. How do I do it with one nozzle? I create a split flow pattern. You see here, same nozzle, but I create a split flow pattern so that I can place a layer like that. Smart way, but have you completely eliminated the rheology problem? No, you still have that issues with shape stability and all of that. In these pictures, it will look very good, but when you start to print, you will have the sideways flow and things like that. So none of these methods are foolproof as of now. Of course, advances and developments will happen, but these are things that people are very actively working on. Continuity across layers. You look at these steel mesh strips, how they have integrated steel mesh strips across layers. So now you start to reinforce across layers because you need reinforced lateral resistance. If you need only axial resistance, I wouldn't care, right? Why would I need this? If you need axial resistance, you would need that. Suitability, I showed you this. The fibers were the best one. Steel fiber links, you could do it, and everything else down the line, not all that good. Permanent formwork, post-tensioned, additively manufactured steel, nails, all of those have their own issues. And then, of course, if you do this, then you can do very similar. We actually have done some work on this, not with reinforcement, but where we can actually redo the, if you want, again, hypothetically. So we did this, and I'm not showing it in this set of presentations. But what we did was, for example, if I'm 3D printing a really load carrying member, and I know that I have the capability to do shape and topology optimization. But if I'm not doing a very efficient shape and topology optimization, if I'm still creating a layered structure, can I start to do a multi-material system? can I optimize the material? One very good material where I want all the good properties, and one not so good material where I don't want that good properties. Can we do multi-material optimization? So we have done this with UHPC and conventional concrete. And so when you do that, and when you design, for example, a beam, you cannot use your conventional beam design example, because every layer will be under a different state of stress. So you have to do a composite laminate theory. We've done laminate theory. We've published that as well. So you can look at that. You can use that same laminate theory idea. So it's exactly the same one, where basically one of the layer is steel. That's it. Your design process is exactly the same, right? One of the layer is steel. So you basically change the material property. And the advantage of doing such a thing is that it becomes very easy to implement in a numerical computational simulation. So you don't have to sit and calculate strain in each layer, stress in each layer, deformation in each layer, force in each layer, equilibrium in each layer. You don't have to do that. You automatically can compute the global values in a continuous loop, and you can optimize the quantity. So that's what they have done here also. Where you put this steel to, again, if you look at a regular reinforced beam, you say that I'm going to put my steel here, you will laugh, right? Really? Is that where you're going to put your steel? It looks like a nice place to put steel where it absolutely is not needed. Lapped mesh specimens can sustain moments way beyond cracking. Like, of course, when you have mesh that's lapped, it can take moments in both directions. Capacity will obviously be higher. Failure modes, cracking for materials like that. Here is another interesting structure. You see here, very interesting structure, and um, bonded steel in voids for global capacity. So bonded steel rebar in voids, and then interlayer shear reinforcement placed during printing for shear transfer. You saw that in like every layer they were placing shear reinforcement, right? So combined system with bonded longitudinal bars and interlayer shear reinforcement. Otherwise, how would you do? Oops, sorry. In a box girder, you will have shear reinforcement also this way, but you don't have space for shear reinforcement there. So they're basically doing that shear reinforcement in these layers, like placing the shear reinforcement in the layers. Post-tension, bonded bars, unbonded post-tension beams, lots of things that you do in a traditional manner. In-nozzle textile embedment, that's another thing that again, see here, same two-nozzle story that I said. Because you have to put in a textile here, you develop a nozzle that has a space for it, and they have done it craftily in several different ways. So concrete will come through, and then it come in as two different. So you don't have to have two separate nozzles, one and then branching off into two, to do two layers, so one here and one here, and that's an AR glass textile reinforcement. You can place textile reinforcement along the layers also to get interlayer shear transfer. Rheology, bond and pumping, bond potential. Again, any of these strategies, rheology again becomes important. Your rheology now is a different rheology to account for all of these processes as well. So again, we go back to where we started. Bond slip pull out. So this is another interesting way of using carbon fiber reinforced polymer. So you create, if you have a 3D printed geometry that you want to create, so you have layers that go in and create a unique geometry. At that time, once you have designed all of that, then you go and create a carbon fiber reinforced polymeric mesh like that. And then once you have done a few layers, wherever that is required, just dump in that mesh on top of it and start printing completely on top of mesh. So instead of rebar layer by layer by layer, this is one unique rebar placement strategy where you place that rebar, the carbon fiber reinforced rebar. Again, here it's showing as whatever shape that you have, initial reinforcement scheme, you put in wherever you want. So CFRP, because it is, you can do it ahead of time. You can do that cage. Very similar. You can, it doesn't have to be CFRP. You can do meshes, you can do textiles, you can do all of that exactly the same way. Another another interesting way of doing it. And then how do you print on top of that? Um, all schematic printing way. So how do you print on a curved layer? You see this? Layering curved on top of that. So and then you get extremely high. So sorry, yeah, you do that and look at what kind of load patterns, what kind of failure, because you have different reinforcements, grid scheme, cell skip, all of that. So effectively, the bottom line is you have so many different ways of putting rebars. There is nothing that is a best way and not the best way. It depends on how your structure is, what you want to do. But your best option so far, at least from whatever literature, what we have, the best option is to use fibers so that you're consistent in what you're able to achieve. If you really want rebars, reinforcement in certain directions, then choose your design wisely, choose a rebar strategy wisely, make sure that you design the element carefully, do all the finite element analysis, whatever you do need to make sure that the adequate stress transfer stresses are all taken care of before you do it. But then if you have to do it, there are several different methods that is possible, partly as simple as just putting a layer of rebar, or as simple as putting a vertical rebar and grouting, to putting in a mesh of rebar and changing your nozzle patterns to do through it, or pre-printing rebars and putting them on top, or nails or screws. Lots of different strategies to implement if you ever have to. Um, this is this is the idea of wire arc additive manufacturing. I'm sure you will have a WAM system in campus here, because if you have to build a 3 meter high metal additive manufacturing structure, you will have it. So you can integrate a WAM with 3D printed concrete. That's what I said. But then you're extruding a metal along with extruding a concrete. It has been tried as well in some experimental scenario. I don't know if it has been tried in actual structures. Um, there was a big project to do 20 or 25-meter high wind turbine support structure using 3D printing. Cobalt actually did it with DOE. They started with Oak Ridge, just what they call their caterpillar kind of a printer that's hanging from two wires and doing it. That didn't work. So Cobalt eventually printed it for offshore wind wind towers. They did this, so it was like this structure with a large diameter at the bottom, curving inwards and then building out further. What they did was every um, every 3 layers textile reinforcement for interlayer shear transfer at, I don't remember exactly, after whatever height, um, at every whatever, this was circular, so every whatever spacing at that depth alone to create um, kind of pylons within your structure itself, on which it is 3D printed. So it's basically like a double shell. One, this big outer shell, and this inner shell with localized reinforcements, right? So to take care of, because it was going 25 meters high. So that's what they eventually did, but they couldn't do 25 meters high. I think they have a 3-story high printer, so they can do, I think, 10 or 12 meters high. So they actually did it in 2 sections, so that section 1 and section 2 with a crane, they'll put it somewhere together. I don't know how. So they did reinforce multiple reinforcing options. That's the largest reinforced structure that I know of, a complex structure. Of course, there are buildings that have been built, but all the buildings that have been built has roofs that are non 3D printed. So the biggest flexural members are taken care of. The compression, they took, simply inserted rebars and grouted some places and created stronger walls essentially. But the bigger, complicated rebar structure that I have ever heard about. I haven't seen it. I've read about it. Is this wind turbine, wind turbine support structure? That's the only one that I know. The rest of it, most of it, are restricted to experimental work. Still a lot to develop. So don't ask me too many questions on this because I haven't worked on any of these. I know only as much as you know on this, and I've put in all the references for you to read, get up, or whatever you need. On dot. I told 10:30. It is 10:30. There's some basic questions, sir. Yes. It's very important of cables. Like this textile reinforcement is what it is. So textile reinforcement is like you have you weave things, right? So you have mats that are woven in different directions, so they have good strength in both directions. So it's basically a textile. Fibers, so think about continuous fibers in both directions. You can do well. Cotton silk are the textiles that we use to weave. These textiles could be natural, could be synthetic, like polymeric fibers, could be aramid, could be even wire mesh. You could consider as kind of a textile in pattern. And the thing is, like, how this can be compared with steel fibers to normal reinforcements? So steel fibers have the same tensile strength as steel. Steel is steel, right? So steel fiber has the same tensile strength as steel. Same percentage of reinforcement. No. So when you distribute something versus when you do one reinforcement, that's a completely different strategy, right? So when you put in fibers, you distribute it, which means it is distributed so well that a crack that is forming somewhere and trying to grow will find a fiber somewhere and get blocked and get arrested. Whereas if it's a rebar, remember your reinforced concrete design, your steel will start to take the tensile stresses only when the concrete in the tension zone cracks, and the crack has to go and hit the level of rebar to transfer stresses, right? Which means if you have a 50 cover, you need a 50 crack to get to the steel for steel to start engaging in stress transfer. Whereas in this case, because you've rebars distributed uniformly, you are getting the rebar, and without stresses being developed or cracks being extending that far, you are engaging these steel fibers, which means you don't need this big of a bar to be there because the stresses, its crack is only started to grow. It needs only very little of stress to be released, and it just releases it right there. And then you have to build up again, you find another rebar, build up again, find another rebar. This is like trying to have one strong person resist an army versus lots of little guys resist a lot of little people, right? You will have much lesser effort in resisting cracking when you have distributed fibers. And that is why ACI has come up now with fiber reinforced concrete designs that you can do for slabs on grade. So really, for slabs on grade, if you're doing an industrial floor, even a heavy industrial floor where you will drive heavy machinery through, you don't need to put in steel reinforcement. Fiber reinforcement is good enough. And you don't need extremely high volumes of fiber as well. When you need ductility, now the other thing that fibers do, because they arrest cracks, because they don't let cracks grow further, and because of the fact that cracks are not going to go, fiber is going to engage in that load transfer very, very quickly, you will have, even after the material has cracked, there will be significant load capacity. Think about your regular normal concrete. Once it cracked, load capacity just drops down. It can't take any more load, right? Whereas in this case, with subsequent cracking, there'll be a little bit of load drop, but a fiber will engage, the capacity goes up. Engage, capacity goes up. And even after you reach the peak load capacity, where there is a crack that's gone a significant length, and then the crack is opening, you still are carrying a bit of load. So your post-peak capacity, which is a ductility, right? your ability to carry load and disperse energy even after peak is reached is much more there, which means you are having a much more robust, resilient structure which is not going to collapse immediately. You can save people, you can let people get out of the building before it fails, you can get people get out of the bridge before it fails. So fibers help you design structures that are much more resilient than you can do with conventional reinforced concrete design. Okay. What is cable, sir? You said cable. Cables are basically yeah, basic cables which are things that are drawn. So like your electricity cables, right? So it'll be in a spool that'll be drawn and kept. So they are not rigid reinforcement like steel. They are bendable and rollable. Like 3 mm steel bar. I don't know what the material is. It's probably, yeah, it's probably a smaller diameter, an alloy, but that is rollable. 3 mm steel, 2 mm, up to 2 mm we can go. Any other questions? Hmm? So, like I told you, I've only read what you have read. Okay, so I haven't seen cage type reinforcement. So, basically, three-dimensional. Everything is so rebar 1D, textiles 2D, cage 3D. So now you have reinforcement in 3 dimensions. So basically, think about a curved structure like that. So you will make a cage in a way that you have in 3 dimensions. I don't know how to pump. You may have a special nozzle that goes through whatever, but there is another way of reinforcing. Okay, but you should look at those papers. I haven't seen them. I haven't worked on them, so I'm as ignorant as you in that. Other questions? If not, I think we can stop, take a break, and then come back in 20.